see how to perform the experiment called torsion pendulum. The aim of this experiment is A. To determine the moment of inertia of this inertial disk about an axis passing through its center and perpendicular to its surface. And B. To determine the rigidity modulus of the given wire. That is the rigidity modulus of the material of the given wire. The apparatus that are required for this experiment are an inertia disc, as you can see here, the wire which is very thin, a chuck for mounting the wire to the inertia disc, and another chuck for suspending it from a point. We also need a stopwatch for recording time for oscillations. We also need cylindrical masses like this, which we would be placing near the chuck, very near the chuck, and also farther away from the chuck. These two cylindrical masses here are 100 grams each. We need to have equal cylindrical masses. We also need a screw gauge for measuring the thickness of this wire, and a thread is given to you for measuring the length of this suspension wire, and a scale for finding out what is the exact length by keeping the thread on the scale. You also need a small scale for measuring the distance between the centers of the cylindrical masses. And you also require a fan balance for finding out the mass of the inertial disk. But this mass is very often given to you already, so you need not worry about finding out the weight yourself. Now let us see the formula for finding out moment of inertia by experiment and by theory, and also that of rigidity modulus by experiment and theory. As you can see, moment of inertia of the disk by experiment is designated as I experimental, that is IEXP, is equal to 2m into d2 square minus d1 square into t0 square divided by t2 square minus t1 square. Its unit is kilogram meter square. By theory, we have the formula for moment of inertia as I theoretical ITH equal to capital M into capital R square divided by 2, again in kilogram meter square. And the rigidity modulus of the material of the wire eta experimental, eta EXP, is 8 pi I experimental into L divided by T0 square R power 4 newtons per meter square. And theoretically, this value is eta TH equal to 8 pi I TH, that is the theoretical value of moment of inertia will be substituted in this formula into L divided by T0 square R power 4 Newton per meter square. Remember, R power 4 is occurring in the denominator, and hence the radius of the wire is very crucial in the experiment. We have only given the formula and the symbols. Now let us see the explanation of symbols. Small m is the mass of one of the cylinder placed on the disc in kilograms. D1 is the minimum distance between axis of rotation and the center of mass of the cylindrical mass, and that is in meters. d2 is the maximum distance between axis of rotation and center of mass of the cylindrical mass, that is again in meters. T0 is the time period, that is time taken for one oscillation by the inertia disk without any mass placed on the disk, and that is in seconds obviously. T1 is the time period with equal masses placed at D1, again in seconds. T2 is the time period with equal masses placed at D2, again in seconds. L is the length of the suspension wire in meters. R, which we found occurred in the denominator as power of 4, that radius of the wire is in meters. Capital M is the mass of the inertia disk in kilograms. Capital R is the radius of the inertia disk in meters. Now let us see the same thing what you saw as the instrument in a diagrammatic form, so that we find an explanation for what is D1, D2 and L here, which we are anyway going to measure. Here you can see this is the cylindrical mass. You can see it is placed at equal distances, at very close distance from the axis. It is shown slightly away, but when we do the experiment we place it in contact with the chuck. Both the cylindrical masses at the closest distances are placed in contact with the chuck. So you can see from the axis of rotation up to the center of the mass, that distance is D1. And when you keep it at a farther distance, the distance between the axis of rotation and the center of the cylindrical mass is D2, and the length of the suspension wire is from the point of suspension to the point where it is affixed to the chuck near the inertia disk, that is L. Now let us see how we perform the experiment. First, take the wire given to you for measuring the length of the suspension wire, keep it like this at one end of the chuck, and then up to the point of suspension find out what is the length. You have a scale, keep it on the scale from the left end of the scale, that is the 0, and up to what point you have measured it. Note down the length in the column provided in the tabulation in your manual. The next thing you have to do is measure the diameter of the wire, and hence you can find radius. So for that you are provided with a screw gauge. The operation of the screw gauge is already mentioned to you. First note the zero error and zero correction of the screw gauge. Then keep the wire in between the two surfaces of the screw gauge. Do not overturn the screw gauge, because if you start turning it too much and show all your power on it, the wire will start compressing and you will not find the correct diameter of the wire. So you have to stop the rotation of the arm of the screw gauge when you feel the surface of the wire. At that time, note the pitch scale reading and also the head scale coincidence. Now here there is a common mistake which everybody does. Generally the pitch scale 1 is slightly visible, so people write the pitch scale reading as 1 instead of 0. This is a common mistake which is also committed when we actually read time in our wall clock. That is, the time may be 2:59. That is, it is nearly 3 o'clock, but people often make the mistake of telling that as 3:59 because the our hand has crossed the 2 marks slightly, but that is not correct. It is actually 2:59 or nearly 3 o'clock and not 3:59. Similarly, here also the pitch scale reading will be only 0 and not 1. In case you have a doubt, you can approach the concerned staff member and verify. So please do the diameter of the wire first before starting the experiment. Verify whether the screw gauge reading is correct. Only then proceed with the experiment. You have to take the readings at 2-3 places which are slightly farther away from each other and record it in the respective tabulation given to you already in the manual. So since you have found the diameter, half that value will give the radius, and you can convert it to meters and keep it aside. Now you are ready to start the actual experiment. So what we have done, we have found out the length and we have found out also the radius of the wire. Now our business is to find out the time period of oscillation without masses, with masses at closest distance and with masses at farthest distance. So we have to find out T0, T1 and T2. That is time for one oscillation. So just by taking one oscillation, accuracy will not be there. So we have to take time for 10 oscillations, then convert it to time for one oscillation. For finding out time for 10 oscillations, we first make a mark on the inertia disk for reference like this. It is already marked sometimes, but if it is not marked, use a marker pen and make a mark like this, so that it is very clearly visible to you. Then verify the stopwatch that is given to you if it is working properly. Do not start the experiment without verifying the stopwatch, otherwise it will be a waste in the middle to stop. So how do you verify? See, this is a razor stopwatch in which you have minutes, seconds and then 0.00 seconds. That means you can read the time up to 1/100th of a second. So you have to record all the divisions on the stopwatch whenever you do the experiment. Do not round off any division. So how do you check the stopwatch? See whether you press the mode and see whether it is in the stopwatch mode, and then to start the stopwatch, press start stop and see whether it is running properly. So again stop it. If when you press the stop button, the watch must stop playing, and then you have to bring it back to 0. So at that time press the reset button. That is on the left hand side of what I am showing, left hand side of the instrument of the watch. So once you have confirmed that the stopwatch is working properly, go to torsion pendulum for recording oscillations. So you can see that I am now slowly placing my fingers on the chuck and giving a small rotation. The torsion pendulum, the inertia disc should not wobble like this, nor should it oscillate like this so fast. It shouldn't go like this. If it is going like this, it is wrong. The whole experiment will be wrong, because your formula holds good only for small oscillations, because you know the angle of rotation theta will be equal to sine of theta only for small oscillations. So to correlate experiment and the formula, you should oscillate the pendulum very slowly. So that means the angle of rotation should be very, very small. That means around 30 degrees only. So that is what I have done now. You can see I have stopped the wobbling and I am allowing it to rotate very, very slowly. You can see it is a very small oscillation. You can see this mark, it is going from there to maximum. This place you can see the oscillation is very small. Do not start taking readings now. Allow the torsion pendulum or the inertia disc to oscillate for some time. Let it attain freeness. After that we have to start taking the time for 10 oscillations. That is why we have taken the reference. Now what is one oscillation here? How will you count one oscillation? So let us say this is the reference I have taken. So let it come back to the position nearby me. I will start that as my starting point. You can see here now this is the starting point, this is 0. I start the stop clock here, this is 0. It goes there and then comes back to the same point. This will be one oscillation. And it goes back, again comes to the same point, second oscillation. Like this, we have to count 10 oscillations. So what is one oscillation? I will repeat. I start here, I go there and then come back to the same point. That is, you start your relay race, just like your relay race. You start the relay race at one point and you come back to the same point. So start, go to the ending for another place, then come back to the same point. That would be one oscillation. So count 10 oscillations like this and then that is going to be the trial number 1. Now for trial number 2, do not stop the torsion pendulum. Stop only the stopwatch. Because this will keep going on. Do not again and again start and stop the torsion pendulum for 2 trials. Now let us see how you actually record the time. Now we will start. This is the turning point. I have started. This is 0. It goes to the other point. You can see the oscillation is very small. Now it comes back here. This is 1. Two. 3, 4, 5, 6, 7, 8, 9, 10. So you stop the stop clock, stopwatch. Do not stop the inertial disc. So another precaution is very often we have seen people simply stand near the torsion pendulum and it oscillates. They start the stop clock correctly, but their eye is not held to the reference point. They simply don't bother, they keep the stop clock here, they see somewhere here and there, so they would have missed out on oscillation. So finally all the time will be wrong and you have to redo for unnecessary reasons. So remember, concentrate on the reference line what you have kept. Keep your eye only on that. You should not be distracted to any other place. Only then the timing will work out correctly. It is very difficult to make an error in this experiment unless you are distracted and look somewhere else. So be very careful. Now let us see what is the reading, okay, what we have recorded. So this is only a sample reading, it may be different also. So the reading here is 2 minutes 38 seconds and 0.41 seconds, which means it is 2 minutes 38.41 seconds. And what will that be? 2 into 60 is 120 seconds. 120 plus 38 is 158. So the timing here will be recorded as 158.41 seconds. And this is trial 1 for T0. And what is this time for 10 oscillations? So 158.141 for 10 oscillations means this divided by 10 will give time period, that is time for 1 oscillation. So it will be 15.841 seconds. So that is our T0 value for trial 1. But now we will have to also do the trial 2 in a similar fashion. Repeat it in the same manner by pressing the split reset button so that you bring it back to 0, and then repeat the trial 2 in the same manner. Now we have to do for T1 and T2. So how do we do T1 and T2? The same way, have the same mark only, but keep the weights diametrically opposite and close to the chuck. It should be in contact with the chuck. Do not keep it like this and all. Keep it diametrically opposite. Again, repeat the experiment, that is time for 10 oscillations. That is trial 1 and trial 2 for T1. Then keep it at the farther distance and repeat the experiment for trial 1 and trial 2, that is T2. Remember, when you are doing the experiment itself, verify that T0 will be less than T1 and will be less than T2. That is, the timings will increase from without mass to with mass with closest distance to with mass with larger distance. So when you are doing itself, please verify the readings and record the readings up to the last decimal there, what is indicated. Now we have to measure what is D1 and D2, that is what is left out, and also the diameter of the inertial disc. So to measure D1, what you do is, it's enough if you have a small scale. Don't measure D1 directly, it's difficult. So use a scale with the proper calibration and keep the 0 mark of the scale at the center of one cylindrical mass and see what is the reading at the center of the other cylindrical mass. Obviously this will be 2D1. The 2D1 value is already listed in the tabulation. You can record it there. Okay. So if 2D1 is 5.3, then D1 will be 5.3 divided by 2. So we will take some other value. Instead of 53, we will simply take it as 50. That is 5 centimeters. So 5 centimeters means it will be 5 divided by 2, which is 2.5 centimeters or 0.25 meters. Again, in a similar fashion, keep it at the farthest distance, that is concentric with the circumference like this, and similarly record 2D2 and hence D2. So the next thing we need for theoretical value of moment of inertia is the diameter of this inertial disc. You can turn this back side and then use a scale and measure the diameter of the inertia disk, and hence the radius will be half of that. So the mass of the inertia disk is given to you already. It will be listed at the back of the inertial disk, or it will be pasted on the wall. Otherwise, you can approach the attendant or the lab assistant for the mass. We now have all the data that are required for the experiment. Let us see now a sample calculation of how you are going to arrive at the result. Remember, this is only a sample calculation, and the values may be totally different when the wires are given to you. The length may be different, the wires may be steel or it may be brass. So this is only a sample. So remember, write your own reading whatever you get in the laboratory. We can record the observations whatever I told you earlier, how we perform the experiment as follows. Length of the suspension wire, the value here is 68 into 10 power minus 2 meters. You can see position of the masses, that is without masses. We have taken time for 10 oscillations for trial 1 and 2. It's not the same what I have told you earlier. It is only a sample reading what I have taken. 180.90 is for trial 1 and 180.55 is for trial 2, and the mean of these two is 180.72 seconds. And time period, as I told you, is time for one oscillation, and 180.72 divided by 10 is going to be equal to 18.072 seconds. Similarly, the value of D1, that is with masses at D1, and this is going to be 0.024 meters, that is masses at the closest distance. Again we repeat the experiment for T1, and masses at farthest distance, that is D2, 0.059 meters. The experiment is repeated. You can see the time for one oscillation T1 is 18.466, which is greater than T0, and similarly T2 is 20.049, which is greater than T1. You can see therefore that T2 is greater than T1 is greater than T0. So we have already pre-recorded the screw gauge readings also with your zero error, zero correction, etc. The zero error is -5 divisions. So the zero correction is +5 divisions. So +5 divisions will turn out to be in millimeters. +5 into 0.01 mm, which is the least count of screw gauge, and that is going to be 0.05 mm. Now we can record the screw gauge reading as follows. You can see pitch scale in millimeters, head scale in divisions, then observed reading in millimeters, and then corrected reading also. You can see it is 0.40 and then another 0.05 added, which is 0.45 millimeters. In this case all the readings appear to be similar, but it need not be. It may be different. For example, you may get 0.40, then 42, 44, etc. So you will have to correct them. Accordingly, whatever you get, then divide by 2, you will get the radius. Now all the data that are required have been listed here, and T0, T1, T2, D1, D2, M, L, D, small r, capital M, capital D, and capital R. We have all the data here that are required for the calculations. So the experimental value using the formula already given is calculated like this, and we get the value as 3.1127 into 10 power minus 3. Remember to write the units. It is kilogram meter square, and report this value always in 10 power minus 3. You can also verify with the theoretical value, which is m r square by 2, that is all capitals, and we have the value as 3.1048 into 10 power minus 3 kilogram meter square. The rigidity modulus of the material of the wire, eta experimental, again is calculated using the formula already given to you. And remember, we have 0.225, that is r power 4. 0.225 into 10 power minus 3 meters is what we have, and that to the power of 4. So do not use this 10 power in the calculations of the calculator. Very often it creates a mistake. So you can have 10 power minus 3 to the power of 4 will be 10 power minus 12 in the denominator. So if you take it to the numerator, it becomes 10 power plus 12, and that plus 12 with this minus 3 will give you a plus 9. And here I have already converted the length to meters, so 0.68, there is no problem. Otherwise there will be another minus 2 there, you will have a minus 7. After that, whatever you get, you can actually do the computations. Again here, first compute the denominator in the calculator, take the inverse, then multiply by the numerator. You will find you will not make any mistake if you adopt this procedure. I repeat, do not use 10 powers in the calculator. Keep it aside separately. So you have 10 power minus 3 to the power of 4 is 10 power minus 12 in the denominator. Take it to the numerator, it becomes 10 power 12. You have a minus 3, so it becomes 10 power 9. Do the denominator separately, take the inverse, then multiply by the numerator. Then you will get the correct answer. Remember, the rigidity modulus should always be reported in power of 10. You will always get the answers in power of 10. So here we find the value is 6.352 into 10 to the power of 10 newtons per meter square. Similarly, the theoretical value also has to be done. Only thing, in experimental what we did, we substituted experimental moment of inertia. In theoretical computation, we substitute theoretical value of moment of inertia. So that value turns out to be almost similar, that is 6.336 into 10 power 10 Newton per meter square. So we report the result as follows: the moment of inertia of the disc by experiment is so much and by theory is so much. And similarly, the rigidity modulus of the material of the given wire by experiment is 6.352 into 10 power 10 newtons per meter square, and by theory is 6.336 into 10 to the power of 10 Newton per meter square.